I'm going to review some basic physics concepts so that later lectures will be understandable if you haven't studied physics before. So a lot of vocabulary if you haven't seen this before. Force is equal to mass times acceleration. Force and acceleration are vectors. Acceleration is the time derivative of velocity. Mass times velocity is something we call momentum, but traditionally call it p. And there's a very specific kind of thing that happens that we'd like to look at, which is what if the integral along the actual path of the particle from a certain time to another time of the force dotted with how you travel. This is a line integral, and one way to evaluate it is to do this regular ordinary time integration. R is a nice name for the position as a function of time. It's also a vector, but its total time derivative is just the velocity. So you might think of this as f dot v. And you might think there could be lots of different solutions. If someone just told you that at a particular time you were located somewhere, so r of t1 equals r1, r of t2 equals r2, you might think, well, I don't know what the initial velocity is, so maybe there's lots of ways to get from here to there. And if it doesn't depend on the path you took, then this vector field is called conservative. And there's a very important result that says, if f is conservative, there exists a scalar field this funny backwards E just means there exists. So there exists V, and it's going to go from, let's say R3 if this is conservative everywhere. Scalar just means it gives us an output a real number, not a vector. So the force field at every point would be a vector. So every point in space gives you a vector. This just gives you a scalar, such that the gradient of the scalar field is just a force. Remember, what's this guy? It's a vector whose components are going to be the partials of v in each of the three directions. So a partial, remember, you just think this vector, this field V has three inputs, x, y, and z. Imagine that you hold y and z constant, and you just vary one of them. Well, hey, now it's like an ordinary one input function, and you just take the regular derivative you're used to. Well, once you have this, you can simplify this equation over here. You can put in the gradient v, big V. I apologize about all the V's and stuff. This is just traditional. In fact, this is called potential in physics. So we've got the gradient of V, dotted with V, do that integral. And now we have a neat result from line integrals. It says if what you're integrating is the gradient of something, this is just going to be equal to the difference of the 2 points. So we're going to have here's the line integral, so find the evaluation here. So that's v of r of t2. Remember I said you could take lots of different paths? Well, we're considering the paths that end at a particular place, r2 here. So there's r2. There's r1. So indeed, when you integrate this quantity, f dotted with the direction you're traveling, you do get a difference, the difference between the potential function at those 2 points. In physics, we like to have conserved quantities, so this is something that's not conserved. Unless these two happen to be the same, you're going to get something that changed from t equals 1 to t equals 2. So we correct this by adding another term instead we consider potential as a function of space. We also add to it 1/2 the mass times the velocity as a vector. So square it. You can also think of it as being dotted with itself. And I'm going to call this the energy. The position is changing potentially at all kinds of different times, and so the velocity could be different. So this is actually a function of time. This is a function of space. Over here I didn't write it as if it was a function at all, so you might think this is really poor notation. The whole point is it's going to be conserved, so it doesn't matter. As we go from two different times, we end up in two different places, but the change in this will be counterbalanced by the change in this. So this number will be the same for all times, as long as it keeps traveling along this way. As long as force is related to the motion, according to this way, it will be fine. And I'm going to pause and check this to see how loud I've been talking, whether or not the microphone's picking anything up, whether or not the words are legible. I'm looking at a tiny screen, so even when I check it, I could still be wrong. But it's not very deep yet. We'll get more fun.